Okay, hello everybody. So in this short lecture, we will continue our discussions on vector spaces and look at a little more properties of the vector space, beginning with what is called a span of a vector space. So say I have a couple of vectors like denoted by in coordinate representation by 1, 2 and 1, minus 1. So any combination of a number of vectors or a linear combination by means of vector addition. So when I say vector addition, so these vectors will belong to the vector space V, and scalar multiplication. So these are the guys which will come from the field F, of which the vector space V is defined. And in most part of the course, the field will simply be the real line R. Okay. So I take these two vectors A and B, and I can write it as a linear combination, say 2 twice 2A plus 3B will give me another vector. So C is said to be a linear combination of vectors A and B, and these numbers 2 and 3 can be any arbitrary number from the real line. And in general, given n vectors V1 till Vn, I can write any linear combination of K1 times V1 plus K2 times V2 and so on until Kn times Vn. And this case need not, well, they can, some of them can be 0, some of them can be non-zero, and so on. Okay. So this leads us to something called linear independence of vectors. Right? So I'm writing down linear combinations of vectors and so on. So let's start again with vector field V defined over a field F. Okay, and just let me just randomly choose n vectors V1 to Vn from this vector space V. So this set of vectors are called linearly independent. Right, so this is the keyword. If there exist scalars, again these scalars come from the field F, again could be the real line, such that if I write it as K1 V1 plus K2 V2 equal to 0, this necessarily implies that all these numbers are 0, right. So again let's repeat this again, right. So I have this set of n vectors, and these vectors are called linearly independent if and only if there exists this scalars Ki, I going from 1 to n, such that whenever this relation holds, it will hold if and only if these numbers K1 till Kn are 0. Okay. Or just to write, say in words, a linear combination of these vectors, right, all this Vi results in a 0 vector if and only if all these numbers are all the scalar multipliers, the K1, K2, Kn, which are the scalar multipliers for the vectors V1, V2 until Vn respectively, are all 0. We will do some examples as we go through the lecture. So the set of vectors is said to be linearly dependent, okay, if there exist scalars Ki, I again from 1 to n, not all 0. Right? So here everything was supposed to be 0. Here you can have, say, K1 is non-zero, K2 is non-zero, and all others can for example be 0, such that I can write these vectors in this way. Okay. So here the necessary or if and only if condition was all this k should be 0. Here, well, the case all of them need not be 0, all of them can be non-zero also, right. Okay. So now this leads to, okay, what do we do with this n vectors if they are linearly dependent, if they are linearly independent, and so on. So is there some more information inside this, or why do we need the notion of linear independence or linear dependence? Okay. So this nice property called the span. Okay. So let again start with a vector space V, and again I just collect this set of n vectors, could be a subset of V, a proper subset of V also. Okay, it cannot be a proper subset of. So I am just taking some n vectors of V. Then the set S spans V if every vector can be written as a linear combination of vectors coming from S. Say any arbitrary vector V can be written as a linear combination. What did we mean by linear combination is something like this. just multiply these vectors by scalars and some scalars and add them up. So, if every vector v can be written as a linear combination C1 V1 plus C2 V2 until C1 E1 C and Vn, right, then what we say that S spans the vector space V. Okay. So, say look at this right. So, I have in 2-dimensional space I have 1 0 and 2 1 and say 0 1 as 2 vectors. Okay. Now, well, does this span the full R2, right? If I just draw them in coordinates that we are familiar with, say I call them the x and y axis, 1 0 would be the unit vector in the x direction, 0 1 would be the unit vector in the y direction. Now, give me any vector, say something like this or something like this or something over here or something, just say something like this. Can I write any vector as a linear combination of these two vectors? The answer is yes, right. That is what high school coordinate geometry teaches us, right. So, the answer here, given V1 is 1 0, V2 is 0 1, does it span the full dimensional space R2? The answer is an obvious yes. Okay. Now, similarly look at the second one, right. So, I have vectors 1 0, 0 1 and I have another guy sitting here 2 and 3. Does this span the space R2? Well, I can simply draw, this is my as usual 1 0, this is 0 1, 2 comma 3 might just be somewhere here. So, can I write any vector in R2 as a linear combination of this? Well, just let me just look at 4 and 6, right. I can write this as 2 with V1, that is 1 0, plus say 3 with V2 and V3, 1 times V3 that is 2 3. So, this will give me 4 and 6. Okay. So, I can write this vector 4 and 6, and similarly with all other vectors I can use these 3 vectors or some combinations of them to write any vector in R2. Say I can even write say vectors like -4 and 6 and so on, right. So, everything else can be written in terms of these 3 vectors V1, V2 and V3. So, answer here is also an obvious yes. Okay. Now, what about the vectors V1 and so if I have 2 vectors which are like 1 1 -2 -2, do they span the space R2? So, let us say can I write say for example the vector 4 comma 6 as some linear combination C1 with 1 plus some scalar C2 with -2 -2. So, you can just do solve some simultaneous equations here and find that there exists no C1 and C2 such that the above expression holds. So, what about the vectors 1 1 2 2 -2 -2, do they span the space R2? The answer is no. Okay. So, okay, does this span some lower dimensional space? Does this for example span say R1? Well, the answer is yes, but we will come to that a little later, right. So, what if it does not span the space R2? Does it span a lower dimensional space? Well, the answer here is yes, but we will look at it a little later. So, here we are just looking at what does span mean, and then what is the role of these vectors V1 till Vn in determining if they span my n dimensional subspace in general or 2-dimensional subspace in these 3 examples. Okay. So, this leads to something called a basis of a vector space. So, if I look at, so something doesn't fit here well, right. So, here I have these 2 vectors span R2. I can say, well, these 3 vectors also span R2, and if I write say one more vector V4 called say some say 1 1 for example, right. So, this will also span R2 and so on, right. However, if I add another vector here which is called say minus 20 and minus 20, this may not span R2 and so on. So, what is going on here? So, does it really mean that if I add if I add vectors in this third problem arbitrarily, does it lead to R2? Well, it may answer may be yes or no. And what happens? So, why do I need 3 vectors here when I can just do the entire span with 2 vectors? So, that leads to some kind of compact definition of the span and these vectors from V1 till Vn. Okay. So, again we start with a vector space V over a field F. So, this is a vector space and this is also usually called as a linear space. So, we will use this word interchangeably and they would mean the same. So, the set of vectors B1 till Bn is called a basis of V if B, the set of n vectors, span V. Okay. Now, that is the same as here, right. So, this statement and the one here are same. However, there is something important to add here, right. So, again from the definition of span, any vector V which comes from this vector space capital V can be written as a linear combination of these basis vectors, right. So, going back to this example, well, this is also the span, this is also the span. Now, which of them are what are called as basis vectors? Does this V1 constitute basis vector, or does V1 and V2 constitute basis vectors, or V1, V2 and V3 constitute basis vectors? So, in addition to this definition of span to define a basis, what we also need is that these vectors are linearly independent. This is important because here I just find, okay, are there n vectors that span the entire space, could be R2, R5, R6, R7 or whatever. Now, for example, here this plus this is enough to span R2, whereas this is like unnecessary, right. It is not required. I can still I can do away with this, right, and still have that V1 and V2 span the entire of R2. Okay. So, an additional condition that we impose such that this set is not too large, but still large enough to span the entire space is that they should be linearly independent. Okay. Now, the point of this is, okay, so here you can just look at it, right. So, here are V1 and V2 linearly independent in the first case? Right, we need that one, right. So, they are, so the answer here is yes. So, here are V1, V2 and V3 linearly independent? Well, the answer is no. You can check that. You can always write V3 as 2 times V1 plus 3 times V2. Therefore, you can simply just throw this out and say, well, V1 and V2 will span my entire R2. You can also alternatively throw V1 out and take V2 and V3. This will also span the entire R2. Whereas here I just have 2 vectors, but they still do not span the entire R2. That is because V1 can be written as a linear combination of V2 can be written as minus 2 times V1. So, this is a linear combination, right. So, what are these linear combinations as we saw earlier? So, if I rewrite this again, so I have twice V1 plus V2 equal to 0, okay. And here not all the coefficients are 0, right. So, that is what the definition says, right, of linearly. So, these 2 vectors V1 and V2 in this case are linearly dependent because there exists coefficients ki which are not 0 such that this relation holds, okay, here, okay. Whereas, in the same thing in the first case I can never write say some constant a1 times 1 0 plus a2 times 0 1 equal to 0. When is this possible? This is possible if and only if a1 equal to a2 equal to 0. You can solve them as simultaneous equations. if you don't understand what I am trying to say over here, right. So these are a couple of examples of linear dependence and independence, how they are related to the span, and from the span how do we define the basis of a vector space. Okay. So these numbers k1 till kn, which come from the space from the field, which again will be the space of real numbers throughout the course, will be these are called the coordinate representation or the coordinate vector v with respect to the basis b1 till bn, which means that I can write v as just this vector, sorry, k1 till kn. Okay. So these ki's are called the coordinates of v with respect to the basis bi. So this will be called as the first coordinate, and similarly this will be called the nth coordinate. Okay. So the number of the basis vectors b1 till bn is called the dimension of the vector space, right. So we go back to these examples here. I have two vectors v1 and v2. These are enough to define R2, and therefore these two are, so the dimension here is just 2. Similar, even though there are 3 vectors here, I just take the minimum number of linearly independent vectors and the dimension is still 2. Whereas here, well, it is not true, right. Okay. So the number of basis vectors b1 till bn which span v and which are linearly independent, these two conditions. So this condition here and this condition here are important, and this will be called as the dimension of that vector space. Okay. So an important and interesting question to be asked is the representation of a vector unique with respect to a given basis? So what does it mean? That can there be another set of coordinates k1 prime till km prime that represent the same vector v with this basis? So what is given to us is the following. So I have a vector v which can be written as k1 b1 until kn bn, right, with respect to the basis b1 till bn, and then the coordinates or the coefficients are k1 till kn. Now the question here is, can I write the same vector v as some other coefficients k1 prime b1 plus kn prime bn, right. So the question that we want to answer is, do there exist two distinct coordinate representations for the same vector defined with respect to the same basis of a given set of bases? Okay. So is this true? So this is what we want to answer. Well, I don't know, so let's assume this to be true. Okay. So if this is true, that v can be written in this way and v can also be written in this way. So if this is true, then I can just subtract and get the following, that 0 is k1 minus k1 prime b1, k2 minus k2 prime b2 all the way till kn minus kn prime bn. Okay. Now, what do I know here is that if I assume this to be true, then k1 is not equal to k1 prime. Okay. Now, I have 0 here on the left hand side and a set of some new vector here, right, plus bn. Okay. Now, let us go back few slides, and so if k1 is not equal to k1 prime, then this is a different color here. Okay. Then this will not be 0, this guy will also not be 0 until here. So, none of these coefficients are 0, right, because we assume that these are distinct, right. So, this is the assumption. Okay. Now, let us go back to a few slides and look at the definition, right. So, of linear independence. So, I start with, so if V1 till Vn are linearly independent, then this is 0 if and only if these coefficients are 0. Okay. On the contrary, a linear dependence would tell me that, well, for some non-zero vectors, so sorry, for some non-zero coefficients k1 till kn, something like this holds true. Okay. Now, here, now the question I will ask here is, well, so when will this hold true? Right, that k is not equal to k1 prime, but this entire expression will be equal to 0. Well, from the definition of linear dependence and linear independence, it will suggest that this is possible if and only if B1 till Bn are linearly dependent. Okay. What does the definition of span say? Well, the definition of span or the basis is that these B1 till Bn are such that they must be linearly dependent, and therefore, sorry, linearly independent, and therefore, if this assumption were to be true, then B1 till Bn are linearly dependent, which is a contradiction, right. Therefore, I cannot assume this to be true, because then it violates the definition of basis, and therefore, the answer here is the representation of a vector unique with respect to a given basis. Well, the answer is yes, it is unique. So, I cannot have a vector representation k1 till kn and the same vector being represented by say k1 prime till kn prime with the same set of bases. Okay. Now, the question is, well, can there be some other representation from a different basis? Is the basis unique? Well, we will try to answer that. So, if I look at say R3, which is the simplest of all the spaces of what we also spend a lot of time in our earlier calculus courses, standard basis is something like this, right, and this basis is not unique. For example, this is also a basis for R3, and so in the same way there can be infinite basis, right. So, I can represent, so this there could be several other combinations which could give me infinite amount of basis, right. So, this basis is not unique. So, this is what we should remember. So, what is unique is, given a basis, the coordinate representations are unique. So, this k1 till kn will be basis for say some basis, say b1 till bn. However, there could be other basis b1 prime till bm prime, for which the coordinates will be k1 prime till kn prime. Okay. And similarly, I can write down basis for say the set of all 3 cross 3 matrices, right. So, the basis would be 1 0 0 0 0 0, all these zeros here, similarly 0 1 0, all zeros here, and all possible, and all the 9 combinations with this 1 being interchanged 9 times, right. So, this will be a basis for all the space of 3 cross 3 matrices. Similarly, we can write down for 2 cross 2 matrices, and in general I can write down basis for Rn, like say 1 0 0, then I have 0 1 0 0 and so on until the nth vector will be 0 till 1, and of course, all combinations of them in this way. Okay. So, what did we learn is that the basis is not unique, there could be infinite amount of basis, and given a basis there is a unique representation of a vector for that particular basis. Okay, important class of this basis are what are called the orthonormal basis. So, two vectors are orthonormal if they are orthogonal and also of unit length. For example, say these two vectors here, this and this, right? You can actually see that these are orthonormal or orthogonal to each other, that the dot product is 0. Not only that, these two vectors here, all these are of unit length. So, a vector set V is an orthonormal basis if each pair of vectors V are orthonormal. Like for example, if I choose this and this, well, that is not an orthonormal basis, right, because the magnitude here is not 1 and so on. Okay. Now, why is this useful, right? So, it is useful because I can easily find out the coordinates. What is my coordinate representation of a vector? My coordinate representation of a vector is just given by these numbers, right, from the earlier representation k1 till kn. Okay. Now, this can be easily calculated. So, if say for example, I have V as my vector in Rn and a given set of bases, right, then each coefficient ki will just be the vector V times the Bi column, right. So, that is the dot product of V with Bi. Okay, I do not really need to do this. I think this is kind of trivial in its own way, and maybe you can just write down the details of this, right. Okay. So, in the standard basis used as an orthonormal basis because ki is simply Vi, right. So, Vi here would be the ith component of this vector V, or so it is coming directly from here. Okay. So, as a little exercise, you can just find out what is the coordinate representation of vector B with respect to the orthonormal basis, this one, right. I mean, the trivial exercise would be to do what is the coordinate representation with 0 1 and 1 0 and 0 1. You can just try to do this. It should give you some good answers. The hint is you can just follow this rule here. And okay, these are also normal bases because they are orthogonal and then they are also of magnitude 1. Okay, so that kind of concludes the discussion on what is meant by basis, representations of vectors, uniqueness of basis functions or not, and among several others. So, continuing on that aspect, an important topic would be vector subspaces. Okay, what is a subspace or a vector subspace? So, again we start with vector space V defined over a field F, and let U be a subset of V, maybe a proper subset in general. It could also be something like this. Okay. Now, when is U, which is a subset of V, called a subspace of V over F? Okay. So, the answer is, or by definition, that this is true if U comma F, again U defined over the field F, is itself a subspace. Okay. Now, how to check if it is a subspace? Well, so loosely speaking, all properties of this V in terms of the addition operator, in terms of the multiplication operator and the distributed property of the multiplication operator over addition and so on, everything should be retained in U, right. So, the first thing is, well, it must contain the 0 vector, and the important property is the closure under scalar multiplication, that if A is in U and I just take some number C in R, then this should also be in U. It should not be in V, right. So, I am just restricting everything to U. It should also be closed under addition, right. So, and in general it could happen that the dimension, so now we know what was the dimension, right, starting from here. The dimension was defined with respect to the basis of a vector space. So, the dimension of U is typically less than or equal to dimension of V. Well, examples could be that the vector 0 0 is a 0 dimensional subspace of R2. if I just look at 1 comma 1, this will just be a one dimensional subspace of R2. You can just try to just plot what are all the possible combinations of this span in R2. So maybe we can just do it here. Right? So if I have a x and a y, I have 1 comma 1, so this is my basis vector, and every vector if I were to write would either be here or here, right. So all vectors which I can represent by this span would just be on a straight line, right, and this therefore is a one dimensional subspace. Okay, or in other more generally a plane in R3. So you just impose a condition, say x equal to 0, that will be a subspace. Important thing is that so the subspace that should pass through the origin, right? That's kind of captured over here. Like if I just draw another line, say for example, whereas this blue line was a subspace, but this red line is actually not a subspace. Similarly, with this one is also not a subspace of R2, because this checks will fail. Okay, so what are the good properties of this? So I will prove one of them and I will leave the second one to you. Okay, check if there are two subspaces U1 and U2 is the union a subspace. Okay, so in much of mathematical proofs, it is sufficient to give one counter example to show that this is not a subspace. Right, so that is also one very useful proof technique. So earlier we saw proof by contradiction, we will just show one counter example. So let me just take R3, right. So I have the x axis, y axis and the z axis. Okay. So individually this is a subspace, right. So the entire x axis is a subspace of R3. Similarly, the entire z axis is a subspace. Okay. Now just do check this check these conditions. Okay, it has the 0 vector. Is it closed under addition? Okay, so let's quickly check that. Let me take a vector which is maybe use a different color. Okay, assuming this is visible. Okay, if I take a vector here and a vector here, well, is this so this is somewhere here, right? So this vector which comes from, so let me call this U1 and let me call this U2, and the intersection or so the union is just these two straight lines, right? Okay, I am not talking of the span of this, I am just saying that the union of U1 plus U2 is just these two lines here, this along the x axis and this along the z axis, x and z, there is no y component. Whereas this vector, which is the result of adding these two vectors, this is not in the union of these two. Therefore, is U1 union U2 a subspace? Well, the answer is no, and this is a counter example to that. Okay, this is easier to show, so I will leave the proof for you. Is U1 intersection U2 subspace? Right, so these are little interesting things that you can like work out by yourself, and these properties will be more than useful in the coming parts of the course. So just to conclude, what we learned were the span of a vector space, the basis of a vector space, and a subtle difference between the span and the basis, right? And that's, I think, should be in your mind in a very you must kind of always remember it by heart. And of course, the notion of a vector subspace, and this we will use these concepts to build upon things related to linear maps and other properties of linear maps called the kernel, the image, and so on. And so that will be the part of the next course, of the next lecture. And yeah, thanks for listening.